After we center drill all of the hole locations, we're going to go and we're going to select the correct drill bit using a tap drill chart in preparation for drilling and tapping our holes. In my example here, I'm going to use a 7/8 14 threads per inch drilled and tapped hole size. So I went and I looked at a chart and it told me I needed a 13/16 drill bit. I have the drill bit, I'm back here at the machine, and I'm going to calculate the RPM. Now, this is the RPM calculation chart that we like to use here at the college, and let's talk about how this works. So the material column, this is the actual piece of material that you're cutting. It's your work piece, your part. So in this instance, we're using mild steel. The next column over, we see a surface feet per minute and HSS, and then to the right we see surface feet per minute with carbide. Well, our drill bit that we're using in this operation is a high-speed steel, that's HSS. So we're going to use this 100 number. What we do with the number that matches up to our cutting tool material and the workpiece material is we plug it into this formula up above. So surface feet per minute, that becomes our 100. So 100 times 4 is our 400 divided by the diameter of our drill bit in this application. Now remember, I said 13/16. Well, I know that's 0.812, the decimal equivalent, but I could also do 13 divided by 16 equals 0.8125. The fractions that you commonly have to solve and break into a decimal, you'll memorize them pretty quick. So that would have been 400 divided by 0.812, and I can add the 5, it's not going to matter. So approximately 492 RPMs. The reason I say approximate is because, well, first, my gearbox goes from 400 to 550, so I don't have the option of hitting the number exactly. And then also, what we've done, I think you should keep your RPM calculation chart inside your binder behind the plastic layer, but I'm going to take it out so I don't think you'll be getting a glare. But what I was going to say about these numbers would be in your machinist ready reference, you would see that instead of giving you a 100 right here, I believe the book has 80 to 120. So to simplify this for students, we've just put the middle of the road number. And this also does not take into account what our cutting tool is. A turning tool on a lathe is going to handle heat and the heat transfer from the chips a lot different than a drill that's going into a cavity where there's not as much room for the heat to escape. So generally speaking, when I'm drilling holes, I'm going to go to the slower RPM selection if my gearbox is limited. And even if I could hit this number and I could put the correct RPM that I just calculated, I know from experience that I would probably be decreasing the RPM. And what you have to work with right now is a very, very limited knowledge of how to tell that things aren't going correctly. But with high-speed steel and mild steel as your material that you're drilling, you don't want to see chips that are any color other than silver. If you're seeing brown chips, that's an indication that you're starting to warm up your cutting tool above its actual level of heat that it can withstand. And if you see blue chips, that means that you are definitely going too fast. But having said that, when you break through the bottom section of your material, the material becomes very thin, you will see the chips change colors. It's going to happen because the material is so thin it heats up really quick. But if I start off in the beginning and I'm almost immediately getting chips that are brown or blue, then I'm going to check my RPM, maybe decrease it, or I'm going to double check my drill bit You know, is this thing actually sharp? Do I have relief coming back from my cutting edge? Things like that. Because this machine right here is strong enough that if I brought a drill bit over here that did not have cutting edges that were performing, it would gladly melt down the drill bit for me. Of course, I'd have to really be not paying attention to have that happen, so that's why we pay attention. All right, I need to position the spindle over a correct location for a drilled and tapped hole. This is the point in your project where if you drill and tap a hole in the wrong spot, then I knock a few points off your score. Pay attention to your print at all times. Now, I mentioned before that we were going to use this little centering tool, and this is going to be an application that we're going to put this to use. If I try to line up to my conical feature with the tip of the drill bit, there's only 2 cutting edges. So it'll locate very accurately in relation to those 2 edges, but on the other axis, the drill can be off location. If I take a tool like this, gently clamp it in my drill chuck, now when I position the spindle over a hole, it very, very positively locks into that location. Of course, I remain my feed pressure down while I tighten my locking clamps, and then I can move the spindle away and do a tool change. So I'm going to change to this Morse taper drill bit. This is a number 3 taper shank. It's smaller in diameter than the spindle. So what I do is I use a sleeve, and this goes from a number 3 to a 4. Just like the drill spindle, I make sure all the surfaces are clean. Line up the tang. I'll give it a little tap. Everything's locked together. Okay, so now I have a question. Were you just watching me do all of those steps and wondering to yourself, why didn't we switch drills and drill after our first center drill, so then we would already be lined up? And the answer to that question is, basically I'm making more work into this project. It would be better if when I was first located, if I did my center drill, if I did my drill, and then I tapped the hole without moving away. That's going to give me the most precise results. But what I'm trying to do is build more lessons into this one part. And it's quite often the case with manual machining that you might be lining up to pre-existing features to make a repair or a modification. So there's my justification to why we're doing this. It's more or less the long way around and the less accurate way. But just remember that if you're making this part and it's for a customer, then by all means, you can just center drill, countersink, or chamfer your holes, and then tap your threads all in one setup. Then you know your position is as good as it could ever be. But we're building multiple lessons into a lesson.